Okay, dear students, today we discuss this Fourier series. Fourier series are infinite series that represent periodic functions in terms of cosines and sines. As such, Fourier series are of greatest importance to the engineer and applied mathematician. To define Fourier series, we first need some background material. A function is called a periodic function if f of x is defined for all real x except possibly at some points, and if there is some positive number p called a period of f of x such that f of x plus p is equal to f of x. The function f of x is equal to tangent x is a periodic function that is not defined for all real values x but undefined for some points. More precisely, countably many points, that is x is equal to plus minus pi over 2 plus minus 3 pi by 2 and so on. The graph of a periodic function has the characteristic that it can be obtained by periodic repetition of its graph in any interval of length p. The smallest positive period is often called the fundamental period. Familiar periodic functions are the cosine, sine, tangent, and cotangent. Examples of functions that are not periodic are x, x square, x cube, e power x, cos hyperbolic x, and natural log of x, to mention just a few. If f of x has a period p, it also has the period 2p because it implies f of x plus 2p is equal to f of x plus p is equal to f of x plus p is equal to f of x. Thus, for any integer n is equal to 1, 2, 3, so on, f of x plus np is equal to f of x for all x. Furthermore, if f of x and g of x have period p, then af of x plus bg of x with any constants a and b also has the period p. Okay, we can revise this. Fourier series are infinite series. It means there could be infinite terms, a series of infinite terms that represent periodic functions in terms of cosines and sines. So in this infinite series, sine and cosine function must be included. As such, Fourier series are of greatest importance. So that is why this Fourier series is have an importance in the mathematics and related field, such that to the engineer and applied mathematician, to define Fourier series, we first need some background material. So what is the background material? We must know what is periodic function. So a function is called periodic function if f of x is defined for all real x. So f of x should be defined for all real values of x, mean for the set of real numbers, except possibly at some points, but it should be it should not be defined for some possible points. And if there is some positive number p called a period of f of x such that f of x plus p is equal to f of x. So a function is a periodic function if it satisfies two conditions. First condition is that it is defined for all real values of x, but it should not defined for some points in real numbers. So that is the first condition. And the second condition is that if there is some points positive points, a positive number p. So this number will be called a period of f of x such that f of x plus p should be equal to f of x. So that then this p will be called a period of the function. So if any function satisfy these two conditions, then we call periodic function. So an example of the periodic function is f of x is equal to tangent x. Is a periodic function that is not defined for all real x, but undefined for some points. More precisely, countably many points. That is, x is equal to plus minus pi by 2, plus minus 3 pi by 2, and so on. So it means uh, if this function more countably many points, that is, so the function tangent of x is not defined over pi by 2, minus pi by 2, 3 pi by 2, then 5 pi by 2, then 7 pi by 2. So odd multiples of pi by 2. Graph of a periodic function has the characteristic that it can be obtained by periodic repetition of its graph in any interval of length p. So this is a periodic function of period p. So because this function is coming down to the x-axis at this point and have the similar curve again at this point. So that is why this is the period of the function, and it's a periodic function because it's a similar after a certain distance and the same distance. For example, if the distance from this point to this point is 1, then the distance from this point to this point is also 1. It should be the same. So the smallest positive period is often called the fundamental period. Familiar periodic function. Familiar periodic functions are the cosine, sine, tangent, and cotangent. Examples of functions that are not periodic are, so these functions are not periodic function, cos hyperbolic x and natural log of x, to mention just a few. If f of x has period p, it also has the period 2p, because 1 implies f of x plus 2p is equal to f of x plus p is equal to f of x plus p is equal to f of x etc. Thus, for any integer n is equal to 1, 2, 3, so on, f of x plus np is equal to f of x for all x. Furthermore, if f of x and g of x have period p, then a f of x plus b g of x with any constants a and b also has the period p. So it means the periodic function has the property of linearity, that af of x can be added to bg of x. Our problem in the first few sections of this chapter will be the representation of various functions f of x of period 2 pi in terms of the simple functions. Number 1, so 1 cos of x sin x cos of 2x sin 2x so on cos n. All these functions have the period 2 pi. They form the so-called trigonometric system. So figure shows the first few of them except for the constant one, which is periodic with, okay. So this is the function, is periodic function of period pi, periodic function of period pi, this periodic function of period pi. So these all functions have the same Period. Cosine and sine function having the period 2 pi the first few members of the trigonometric system except for the constant 1. Okay. So the length between one point to other point is a pi. The series to be obtained will be trigonometric series, that is a series of the form a naught plus a1 cos of x plus b1 sine of x plus a2 cos of 2x plus b2 sine of 2x plus so on. So is equal a naught plus n is equal to 1 to infinite an cos of nx plus bn sine of nx. So a naught, a1, b1, a2, b2, so on are constants called the coefficients of the series. So a series of the form which involve cosine of x and sine of x are called trigonometric series. We see that each term has the period 2 pi, hence if the coefficients are such that the series converges, its sum will be a function of period 2 pi. Now suppose that, okay, now suppose that f of x is a given function of period 2 pi and is such that it can be represented by a series 4, that is 4 converges and moreover has the sum f of x, then using the equality sign we write f of x is equal to a n cos of nx plus bn sine of nx and call the Fourier series of f of x. We shall prove that in this case the coefficients of 5 are the so-called Fourier coefficients of f of x given by the Euler formula. So if a naught is equal to 1 by 2 pi, so the famous Fourier series can be written as f of x is equal to a naught plus summation n is equal to 1 to infinite a n cos of nx plus bn sine of nx, okay, and call phi the Fourier series of f of x. So this is actually the Fourier series of f of x. Okay, so Fourier series of f of x can be written as f of x is equal to a naught plus summation n equal to 1 to infinite a n cos of nx plus bn sine of nx. We shall prove in this case that coefficients are the so-called Fourier coefficients of given by the Euler formulas. So a naught is actually the Fourier coefficient which can be written as 1 over 2 pi, okay, minus in pi to pi f of x dx, and then an is equal to 1 over pi minus pi to pi f of x cos of nx dx, then minus pi to pi f of x sine of nx dx. The name Fourier series is sometimes also used in the exceptional case that phi with coefficients does not converge or does not have the sum f of x. This may happen but is merely of theoretical interest for Euler see footnote. Okay. So this is not important. Okay. Basic example before we derive the Fourier, uh, before we derive the Euler formula, let us consider how 5 and 6 are applied in this important basic example. Okay. Yes, the way we approach and solve this example will be the technique you will use for other functions. Note that the integration is a little bit different from what you are familiar with in calculus because of the n. Don't just routinely use your software, but try to get a good understanding and make observation. So you can also leave this portion. Okay, why are the approximating functions called the partial sums of the series? In this example, always 0 at 0 and pi. Why is the factor 1 by n obtained in the integration important? Okay, periodic rectangular wave. So example 1, find the Fourier coefficients of the periodic function f of x. The formula is f of x is equal to minus k if x lies between minus pi and 0. And if x lies between 0 and pi, then f of x is equal to k, and f of k plus 2 pi is equal to f. Functions of this kind occur as external forces acting on mechanical system, electromotive forces in electric circuits, etc. The value of f of x at a single point does not affect the integral. Here we can leave f of x undefined at x is equal to 0 and x is equal to plus minus pi. Find the Fourier coefficient of periodic function in figure 260. So where is the figure 260? 259. 260, where is 260? So this is 260. Okay, given function f of x, periodic rectangular wave. So this is periodic rectangular wave, and we are interested to find the coefficients for this periodic wave. So the formula for this periodic wave is that f of x is equal to minus k if x lies between minus pi to 0, and it will be positive if x lies between 0 and pi. Solution from 6 points, we obtain a naught is equal to 0. This can also be seen without integration, since the area under the curve of f of x between minus pi and pi taken with the minus sign where f of x is negative is 0. From 6a we obtain the coefficients a1, a2, so on. So where is the 6a? Here is the 6a. So this is the coefficient which we are going to evaluate. 1 over pi minus pi to pi f of x cos nx dx. Okay, so here is a 6a. We obtain the coefficients of the cosine term. Since f of x is given by two expressions, the integrals from minus pi to pi split into two integrals. So minus pi to pi cosine nx dx 1 over pi minus pi to 0 minus k, because here it's defined as if x lies between minus pi to 0, we will use minus k. Okay, and plus if it is 0 to pi, we will use k. So the function is split into two parts, and similarly this limits split into two parts, minus pi to 0, then 0 to pi. Okay, now we integrate this. So integration of cosine is sine of nx and divided by n. Okay, so because we are differentiating with respect to dx, so k stands as a constant. Minus pi to 0 plus k sine nx over n, 0 to pi. Okay, so when we substitute this value 0, sine 0 will be 0, and then sine pi is also 0, and sine pi is 0, and sine 0 is 0, so we will get 0. So because sin nx equal to 0 at minus pi 0 and pi for all n equal to 1 2, we see that all these cosine coefficients are 0. That is, the Fourier series of 7 has no cosine terms. So this is the 7, which is called uh, rectangle series rectangle wave. So and now we can compute the second coefficient. What is the second coefficient? You can see here. So this is bn 1 over pi minus pi to pi f of x sin nx dx. So to determine the Fourier series, you need to compute these three coefficients actually. And when we compute these coefficients, you have to replace here. And then you will get the Fourier series. So the second coefficient is bn 1 over pi minus pi to pi f of x sin nx dx 1 over pi minus pi to 0 and 0 to pi sin nx dx sin nx dx. And now again cos 0 0 sin 0 0. Okay, and uh, cos of 0 is 1. So you can see here k over n pi cos of 0 minus cos of minus n pi minus cos of n pi plus cos of 0. So 2k over n pi. So cos of 0 is 1. Okay, and cos of n pi, it depends on the value of n. If n is 1, then cos of pi, n is 2, cos of 2 pi. So that is why uh, author is left for the different values of n. So 2k over n pi 1 minus cos of n pi. Cos of pi equal minus 1, cos of 2 pi 1, cos of 3 pi minus 1. So it's again periodically you can define as that cos of n pi is equal to minus 1 if n is odd. Okay, 1, 3, 5, so on. Cos of n pi is equal to 1 if n is even. Cos of 2 pi, 4 pi, 6 pi, and thus 1 minus cos of n pi is equal to 2, 0 for odd and equal 0 for even. Okay. So then we have this. For example, if we want to know b1, so n will be equal to 1, b2, so n will be equal to 2, b3, n equal to 3. So we have the different constants. So the function will be of this form. We just have to compute this coefficients b1, b2, b3, and then we will get the series. Okay. So since the an are 0, the Fourier series of f of x is 4k over pi sine x plus 1 by 3 sine 3x plus 1 by 5 sine 5x plus so on. The partial sums are S1 is equal to 4k over pi sine x, S2 is equal to 4k over pi sine x plus 1 by 3 sine x and so on. So their graph seems to indicate that the series is convergent and has the sum f of x, the given function. We notice that at x is equal to 0 and x is equal to pi, the points of discontinuity of f of x, all partial sums have the value 0. The arithmetic mean of the limits minus k and k of our function at these points, this is typical. Furthermore, assuming that f of x is the sum of the series and setting x is equal to pi by 2, we have f of pi by 2 is equal to k equal to 4k by pi 1 minus 1 by 3 plus 1 by 5 minus plus so on. So 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 so on is equal to pi by 4. This is a famous result obtained by Leibniz in 1673 from geometric consideration. It illustrates that the values of various series with constant terms can be obtained by evaluating Fourier series at specific points. So here you can see the behavior of the graph. So first three partial sums of the corresponding Fourier series. Derivation of the Euler formula. So how we can derive these constant. This may be the difficult for you. So we can find the fundamental period, the smallest positive period. Find it for graph. We can repeat this. फोरियर सीरीज क्या है कि इसके ये फोरियर सीरीज को ऐसे डिफाइन किया गया है एफ ऑफ एक्स इज इक्वल टू ए नॉट प्लस एन इज इक्वल टू 1 to infinite. ये सम है. It means के n will be started with 1. So for n is equal to 1, we will have a1 cos x plus b1 sin x. For n is equal to 2, we will have a1 cos nx plus b1 sin nx plus a2 cos 2x plus b2 cos sin 2x. Okay, we can repeat. For n is equal to 2, we will have four terms. a1 cos x plus b1 sin x plus a2 cos 2x plus b2 sin 2x. For n equal to 3, we will have a naught plus a1 cos x plus b1 cos x plus a2 cos 2x plus b2 sin 2x plus a3 cos 3x plus b3 sin 3x and so on. So this is called Fourier series, while the coefficients can be obtained using Euler formulas. So the first coefficient is easy because it does not involve cosine function or cos function. This can be simply evaluated with f of x dx minus pi to pi, and then an can be calculated as 1 over pi minus pi to pi f of x cos nx dx for n is equal to 1, 2 and so on. And similarly, the other coefficient bn can be calculated as 1 over pi minus pi to pi f of x sin nx. Then it is discussed a basic example. The example is a periodic rectangular wave. So periodic rectangular wave is shown in the figure 260. So this is the figure 260. So this is a periodic rectangular wave. Okay. So this periodic rectangular wave is defined as